All right, let's talk about partial derivatives a little bit from 7.4. We won't really do any applications of this, but the main reason to learn how to do this is because you'll have functions of several variables. You'll need to talk about slopes in particular directions. You'll also need to be able to find the minimum or maximum value of a function of several variables, um, because just things in real life are functions of several variables, and you'll need to be able in business to be able to find the maximum and the minimum of those types of functions. But for right now, we're just going to be able to find the partial derivatives, and we'll let you learn how to apply that later on in other classes. So some notation here is that if I write z with a little x beneath it, that's the partial of z with respect to x. Another way to write that is a d that's kind of curly like that, curly delta, d, z, d, x, like that. And just like with other things, I can have something where I do a second derivative like this with respect to x twice, and we can talk about later if we need to do it like this right here would say x then y. But if I did that here first, this would be y of this that I've already done like that. So this would be d2z, and then the y would come before, it looks like before the x there, when I write that notation. So I have to kind of read right to left here in this notation if I have a higher order derivative. So that's just some notation for you. I like the first notation, and I'm going to use it as much as I can because I think it's a little clearer, but some of the problems will ask me to write it the other way. Okay, so it says in problem number 1 to find the first partial derivatives of this function. So first partial with respect to x, everything that's not an x is going to be treated as a constant. So this is going to be just 3. With respect to y, everything that's not a y term is going to be treated as a constant. So this is just going to be 5. Number 3, z equals 6x minus x squared y plus 8y squared. Again, we want partial with respect to x first, so that's going to be 6, and then 2xy, the y gets treated like a constant. This is a constant term to me, is just a 0. Partial with respect to y, that's a 0. That's negative x squared was my constant times the 1 there. And so that's going to leave me with negative x squared. And then this differential with respect to y, that's going to be 16y. Okay, now it gets a little trickier here to say number 5, that I have z I like the notation here of this problem. So ln of x, y is equal to e to the negative quantity x squared plus y squared, and we'll, oh, that's not an ln, that's an h. Okay, so that's an h. So h sub x is going to be, so derivative of this with respect to x is going to be, leave all that alone, like that. Derivative of this part with respect to x is negative 2x. And then h sub y is going to be negative 2y e to the negative x squared plus y squared, like that. Okay, I don't know why that didn't look like an h to me and looked like ln, but had to be a letter. All right. Let's move on to number 15 now. And z is 3x plus 2y, and they just want us to write this notation as dz dx, like so. Partial with respect to x is 3, dz dy. Partial z with respect to y is 2. Let's go on to number 29 now. And w is equal to x y squared z to the, I'll write this as it's on a new sheet here. 29. W equals xy squared z to the fourth plus 9xy minus z. And we want the partial with respect to x is going to be y squared z to the fourth plus 9y. Partial with respect to y, it's going to be 2x y z to the fourth plus 9x. And the partial with respect to z is going to be 4x y squared z to the third. No z's in that piece. That's a 0 minus 1. All right, we'll come back next time, do some more of these, but we're going to evaluate them at a given point when we're done to get a value. So very similar to how we did derivatives, and then we did derivatives at a point. Similar idea here. So we'll come back and evaluate some partial derivatives here in the next video. So see you for the next video.